In mathematics, a functor is a type of mapping between categories which is applied in category theory. Functors can be thought of as homomorphisms between categories. In the category of small categories, functors can be thought of more generally as morphisms. Functors were first considered in algebraic topology, where algebraic objects are associated to topological spaces, and algebraic homomorphisms are associated to continuous maps. Nowadays, functors are used throughout modern mathematics to relate various categories. Thus, functors are generally applicable in areas within mathematics that category theory can make an abstraction of. The word functor was borrowed by mathematicians from the philosopher Rudolf Carnap, who used the term in a linguistic context. See function word. Definition. Let C and D be categories. A functor f from C to D is a mapping that associates to each object in C an object in D, associates to each morphism in C a morphism in D such that the following two conditions hold. For every object in C, for all morphisms and in C, that is, functors must preserve identity morphisms and composition of morphisms. Covariance and contravariance. There are many constructions in mathematics that would be functors but for the fact that they turn morphisms around and reverse composition. We then define a contravariant functor f from C to D as a mapping that associates to each object in C an object in D, associates to each morphism in C a morphism in D such that for every object in C, for all morphisms and in C. Note that contravariant functors reverse the direction of composition. Ordinary functors are also called covariant functors in order to distinguish them from contravariant ones. Note that one can also define a contravariant functor as a covariant functor on the opposite category. Some authors prefer to write all expressions covariantly. That is, instead of saying is a contravariant functor, they simply write and call it a functor. Contravariant functors are also occasionally called cofunctors. Opposite functor. Every functor induces the opposite functor, wherein of the opposite categories to an, by definition, maps objects and morphisms identically to, since does not coincide with as a category, and similarly for, is distinguished from. For example, when composing with one should use either or. Note that, following the property of opposite category, bifunctors and multifunctors, a bifunctor is a functor whose domain is a product category. For example, the homomorphism is of the type COP times C set. It can be seen as a functor in two arguments. The homomorphism is a natural example. It is contravariant in one argument, covariant in the other. A multifunctor is a generalization of the functor concept to n variables. So, for example, a bifunctor is a multifunctor with n equals 2. Examples. Diagram. For categories C and J, a diagram of type J in C is a covariant functor. Presheaf. For categories C and J, a J-Pradesheaf on C is a contravariant functor. Presheaves. If X is a topological space, then the open sets in X form a partially ordered set open under inclusion. Like every partially ordered set, open forms a small category by adding a single arrow UV if and only if. Contravariant functors on open are called presheaves on X. For instance, by assigning to every open set U the associative algebra of real-valued continuous functions on U, one obtains a presheaf of algebras on X. Constant functor. The functor CD which maps every object of C to a fixed object X in D and every morphism in C to the identity morphism on X. Such a functor is called a constant or selection functor. Endofunctor. A functor that maps a category to itself. Identity functor. In category C, written 1C or IDC, maps an object to itself and a morphism to itself. Identity functor is an endofunctor. Diagonal functor. Limit functor. For a fixed index category J, if every functor Jc has a limit, then the limit functor Cjc assigns to each functor its limit. The existence of this functor can be proved by realizing that it is the right adjoint to the diagonal functor and invoking the Freyd adjoint functor theorem. This requires a suitable version of the axiom of choice. Similar remarks apply to the colimit functor. Power sets. The power set functor P set maps each set to its power set and each function to the map which sends to its image. One can also consider the contravariant power set functor which sends to the map which sends to its inverse image dual vector space. The map which assigns to every vector space its dual space and to every linear map its dual or transpose is a contravariant functor from the category of all vector spaces over a fixed field to itself. Fundamental group. Consider the category of pointed topological spaces, i.e., topological spaces with distinguished points. The objects are pairs, where X is a topological space and X0 is a point in X. Morphism from 2 is given by a continuous map f, xy with f equals y0. To every topological space X with distinguished point x0, one can define the fundamental group based at x0, denoted pi1. This is the group of homotopy classes of loops based at x0. If f, xy is a morphism of pointed spaces, then every loop in X with base point x0 can be composed with f to yield a loop in Y with base point y0. This operation is compatible with the homotopy equivalence relation and the composition of loops, and we get a group homomorphism from pi to pi. We thus obtain the functor from the category of pointed topological spaces to the category of groups. In the category of topological spaces, one considers homotopy classes of generic curves, but they cannot be composed unless they share an endpoint. Thus one has the fundamental groupoid instead of the fundamental group, and this construction is functorial. Algebra of continuous functions. A contravariant functor from the category of topological spaces to the category of real associative algebras is given by assigning to every topological space X the algebra C of all real-valued continuous functions on that space. Every continuous map f, x, y induces an algebra homomorphism C. C by the rule C equals phi OF for every phi in C. Tangent and cotangent bundles. The map which sends every differentiable manifold to its tangent bundle and every smooth map to its derivative is a covariant functor from the category of differentiable manifolds to the category of vector bundles. Doing this constructions pointwise gives the tangent space. A covariant functor from the category of pointed differentiable manifolds to the category of real vector spaces. Likewise, cotangent space is a contravariant functor, essentially the composition of the tangent space with the dual space above. Group actions, representations. Every group G can be considered as a category with a single object whose morphisms or the elements are G. A functor from G to set is then nothing but a group action of G on a particular set, i.e., a G set. Likewise, a functor from G to the category of vector spaces, VECTK, is a linear representation of G. In general, a functor GC can be considered as an action if G on an object in the category C. If C is a group, then this action is a group homomorphism. Lie algebras. Assigning to every real Lie group its real Lie algebra defines a functor. Tensor products. If C denotes the category of vector spaces over a fixed field, with linear maps as morphisms, then the tensor product defines a functor C times CC which is covariant in both arguments. Forgetful functors. The functor U, GRP set which maps a group to its underlying set and a group homomorphism to its underlying function of sets is a functor. Functors like these, which forget some structure, are termed forgetful functors. Another example is the functor RNG-AB which maps a ring to its underlying additive abelian group. Morphisms in RNG become morphisms in AB. Free functors. Going in the opposite direction of forgetful functors are free functors. The free functor F, set GRP sends every set X to the free group generated by X. Functions get mapped to group homomorphisms between free groups. Free constructions exist for many categories based on structured sets. See free object homomorphism groups. To every pair A, B of abelian groups, one can assign the abelian group Hom consisting of all group homomorphisms from A to B. This is a functor which is contravariant in the first and covariant in the second argument, i.e., it is a functor ABOP times ABAB. If F, A1, A2 and G, B1, B2 are morphisms in AB, then the group homomorphism Hom is given by phi G phi F. See Hom functor. Representable functors. We can generalize the previous example to any category C. To every pair X, Y of objects in C, one can assign the set Hom of morphisms from X to Y. This defines a functor to set which is contravariant in the first argument and covariant in the second, i.e., it is a functor COP times C set. If F, X1, X2 and G, Y1, Y2 are morphisms in C, then the group homomorphism Hom is given by phi G phi F. Functors like these are called representable functors. An important goal in many settings is to determine whether a given functor is representable. Properties. Two important consequences of the functor axioms are: F transforms each commutative diagram in C into a commutative diagram in D. If F is an isomorphism in C, then F is an isomorphism in D. One can compose functors, i.e., if F is a functor from A to B and G is a functor from B to C, then one can form the composite functor GF from A to C. Composition of functors is associative where defined. Identity of composition of functors is identity functor. This shows that functors can be considered as morphisms in categories of categories, for example in the category of small categories. A small category with a single object is the same thing as a monoid. The morphisms of a one-object category can be thought of as elements of the monoid, and composition in the category is thought of as the monoid operation. Functors between one-object categories correspond to monoid homomorphisms. So in a sense, functors between arbitrary categories are a kind of generalization of monoid homomorphisms to categories with more than one object. Relation to other categorical concepts. Let them be categories. The collection of all functors form the objects of a category. The functor category. Morphisms in this category are natural transformations between functors. Functors are often defined by universal properties. Examples are the tensor product, the direct sum and direct product of groups or vector spaces. Construction of free groups and modules, direct and inverse limits. The concepts of limit and colimit generalize several of the above. Universal constructions often give rise to pairs of adjoint functors. Computer implementations. Functors sometimes appear in functional programming. For instance, the programming language Haskell has a class functor where FMAP is a polytypic function used to map functions between existing types to functions between some new types.